Hello students. In this lecture, I will be discussing with you about comparators using op-amps. Till the last lecture, we have seen different applications of op-amp, and this lecture will be dealing with something much more celebrated applications in terms of better performance and all using op-amp ICs. And one of the name of such type of celebrated application is comparator. It is a circuit which compares a signal voltage on one input of an op-amp with a known voltage called the reference voltage, which is applied at the other input. So I repeat, it is a circuit which compares a signal voltage on one of the inputs of an op-amp with a known voltage that is applied as a reference voltage to the other input. So it compares applied signal voltage at one input with the other input signal voltage, which is actually called the reference voltage. Now, in the simplest form, it is nothing more than an open loop op-amp. This is basically the comparator. So this is open loop op-amp circuit, the basic comparator, and it is having two analog inputs and a digital output. The output may be in positive saturation voltage or it may be in negative saturation voltage. So that means either of the two, either positive saturation voltage or negative saturation voltage, that means it is a digital output. One of the two confirmed state or stable state, and the input is obviously two analog signals. Now the output will be positive or negative saturation voltage depending on which input is larger. Since it is open loop circuit, that means from the two analog inputs, depending on which input is larger and it is applied to which terminal, which input terminal, inverting or non-inverting, the output will be accordingly positive or negative saturation voltage. The comparators are used in circuits such as digital interfacing, Smith triggers, discriminators, voltage level detectors and oscillators. So there are many applications: digital interfacing, Smith trigger. This is there in your syllabus. I will be discussing next about this. Smith trigger is the application of comparator. Discriminator, voltage level detector, voltage detector, oscillator, etc. So these are the areas or application where we can use the concept of comparator. Now the basic comparator, let us move on to see how the circuit diagram looks and how it works. Now the basic circuit is like this. So this is the Vin, the input voltage. It is applied to the non-inverting terminal through a resistance R, and at the other input voltage, that is the inverting terminal, through a resistance R, a DC reference source named as Vref is applied of value 1 volt suppose. So these are the two inputs and the output is VO measured across load resistance RL. And so this is the circuit of basic comparator. You can see there is no connection of feedback between the input and output. So this is open loop Opamp configuration. So that means the basic comparator will work without feedback in open loop, and the fixed reference voltage Vref of 1 volt, which is applied to the negative input, that means the inverting input, will be called here the reference voltage, and the other time varying signal, which is Vin, is applied to the non-inverting input, and it will be compared with the reference. Because of this arrangement, this circuit is called the non-inverting comparator, because the input is applied to non-inverting terminal. So this is non-inverting comparator. Now the operation will be very simple. When Vin is less than Vref, that means when the input signal, let us first draw the input output waveforms, then it will be easier to understand for you. So let us first draw the input output waveforms. So let us take the input waveform as a sine wave, sinusoidal signal like this. So this is Vin, it is having peak value Vp, this is a 0 volt axis, and this is the negative peak value minus Vp. Now over this, since we are comparing this Vin with Vref, so we need to place the V reference in this waveform. Suppose for the first case V reference is positive, Vref is positive for this case we are drawing. So V reference will be somewhere here. So this is plus V reference, which is 1 volt, and therefore it is positive, and this is positive value of 1 volt. This is 1 volt. Okay, now let us draw the output waveform. Now the output waveform will be something, this is VO, this is T, and this is 0 volt axis. So now let us see how the output waveform will come. When Vin is less than V reference, that means this area, you can see from the diagram, this is V reference, this is the level of V reference. When Vin is alternating in nature, which is alternating in nature is less than, that is it is lying within this portion, less than this V reference, that means up to from 0, from t equal to 0 to up to this value, when it is crossing the V reference level, that means up to this much, it will be. Now come to the circuit. Vin is less than V reference, so the inverting terminal input voltage is greater than the non-inverting terminal input voltage. That means the output VO will be minus V sat. So in this case, for this, when Vin is less than V reference, for V reference is positive value, this is case 1, and considering V reference as positive, when Vin is less than V reference, so that means output will be at negative saturation. So therefore VO, since the input voltage at the inverting terminal is greater than non-inverting terminal, so output will be a negative voltage, and since it is working in open loop, so there will be every chance that the output will catch up the negative saturation voltage, which is equal to minus VE. So VO is equal to minus V sat, that is negative saturation voltage, which is something equal to minus VEE. Okay, and this is, we can write it as approximately equal to minus VE, because the voltage at negative input is higher than the positive input. On the other hand, when V in, so if we now mark the minus V sat, suppose this is the point which is minus V sat, and this is the point on the voltage axis, output voltage axis, which is plus V sat. So one is minus V sat and another is plus V sat. So that means initially the output will be starting from this level minus V sat. Up to this value it will be flat. It will be parallel to this time axis. The output voltage will be parallel to this time axis, starting from 0 up to this particular voltage when the alternating waveform V in is crossing the plus V reference level. So up to, from 0 to this point it is at minus V sat. So this is flat. This is horizontal parallel to this time axis up to this dotted line, this dotted vertical line, when it is crossing, when the V in is crossing plus V reference. Okay. Now when V in is greater than V ref, so when it after it has crossed the plus V ref, that means when V in is greater than plus V ref, when V in is greater than V ref, that means now it has crossed the input voltage at the non-inverting terminal, the V reference which is applied, the plus V reference which is applied at the inverting terminal. So now V in is greater than plus V reference. This. So what will happen then? The non-inverting input terminal becomes more positive with respect to the inverting input terminal, and the output voltage will go to plus V, therefore VO will go to plus V sat. Output voltage will catch up the positive saturation, which should be equal to plus VCC. So that means similarly, as because previously it was minus V, now it will catch up plus VCC. So therefore we can say once the V in crosses the plus V reference at this point and it is now working in this area, so within this area, so let us take from this point up to this point, from this point up to this point, take a vertical line, another vertical line from here, and between this the minus V sat will immediately switch to plus V sat when it is just crossing, and it will maintain that level of plus V saturation up to the point when it is once again coming down the plus V, when V in is once again coming down the plus V reference level. And when it is once again coming down the plus V reference level, the output voltage will once again switch to minus V sat. So it will fall down to minus V sat value once again. Okay. So the output voltage changes from one saturation level to another whenever the V in is equal to V ref. So the switching happens, switching between minus V sat to plus V sat is happening whenever V in is approximately equal to V ref. That means whenever the input voltage V in is crossing to go above the plus V reference or come down below the plus V reference, the switching is happening between minus V sat to plus V sat and vice versa. So this is the way this is working. This circuit is working as because the op-amp is connected in open loop. So therefore, in short, we can say the comparator is a type of analog to digital computer. So because we are comparing two analog signals at the input and we are getting two stable standard outputs at the standard form of output at the stage of output, because at the output is switching between two stable standard states. One is minus V sat and another is plus V sat. Therefore it is being acted as analog to digital converter. Now at any given time VO, the waveform shows whether V in is greater or less than the V reference. So for any point of time we can measure that whether it is greater or less than V reference, the input voltage V in, from seeing the particular output waveform. So now let us complete the output waveform. So once again it has come down to here, and it will maintain this and it will for the whole region of this V in, which is less than plus V reference, it will be remain there. So during this whole part it will remain there as it is. Now once again here it is going above V reference, the V in, so it will once again jump up to catch the plus V saturation level, and till the time it is above this plus V saturation level, that plus V reference level, the V in, it will maintain this plus V saturation level. Now once it is crossing again, the V in is coming down plus V reference, this will be switching from plus V sat to minus V sat, and it will stay as it is. So this will be the output waveform for the basic comparator when V reference is positive, and this is the corresponding input waveform. Okay. So the comparator is sometimes also called voltage level detector, because for a desired value of desired value of reference voltage Vref, the voltage level of the input V in can be detected. So why it is called voltage detector? It may be called voltage level detector because by merely seeing the output waveform we can immediately predict that at any point of time t, whether at that time the V in is greater than V reference or it is less than the V reference. So we can detect what is the actual voltage level that is being applied at the input. Okay, that's why it is also called, this application can also be called voltage level detector, or this concept of comparator, basic comparator, can be used to explain the work of voltage level detector and also analog to digital converter. So this basic application has confirmed two further applications of comparator. One is analog to digital converter, and another one is number 2, voltage level detector. So this is why, by understanding the operation of basic comparator, we can definitely explain our thought for analog to digital converter and voltage level detector using this basic knowledge of comparator. Now in the if we want to draw the waveforms when the V reference is negative, so let us draw that first. So this is the input voltage as we have seen in case of the previous, and based on this input voltage, minus V reference is shown below the time axis, that is below the 0 volt axis. Okay, so this is 0 volt axis, below that minus V reference has been shown, which is minus 1 volt suppose, and this is the peak value of V in Vp, and this is the peak value minus Vp. So therefore, if we now want to draw the output waveform based on this, this is Vo, we should be getting the output waveform like this. Now if this minus V reference is being applied with respect to ground, which is negative, with sinusoidal signal applied to the non-inverting input, the output waveform will be case 1 when V in is greater than V reference. So this is case 1, and we have considered V reference as negative. Okay, so now when V in is greater than V reference, when V in is greater than V reference, that means you can see it is this portion starting from this 0, and for all this area, all this time, it is greater than V reference. So up to this point, we are considering up to this point, what will happen then? That the voltage, now let us once again move on to the circuit. V in is greater than, V in is applied here, non-inverting terminal, V reference is applied at here. V in is greater than V reference, that means non-inverting terminal input terminal voltage is greater than inverting input terminal voltage, so output will be at positive saturation. So VO will be equal to plus Vsat, which is approximately plus VCC. So therefore, if we draw the waveform, it should be lying over this up to this point, this red line, this vertical line, this is plus Vsat. It will maintain this level. Now once after this point till this point, the V in is less than V reference. So when V in is less than V reference here in this case, therefore VO will move immediately switch to minus Vsat, which is equal to minus VEE approximately. So once again what it will happen, this will be switching to take the new level and maintain till it is once again, the V in is once again moving up the V reference level. So this is nothing but minus Vsat. So this is plus Vsat and this is minus Vsat. So this is the way it is happening. So here once again, when it is at this point, when it is moving once again up, the V in is moving once again up the V reference voltage, it will switch to plus Vsat, and it will maintain that till the time it is coming here, coming down here, that is from this point up to this point, it will maintain like this, and it will switch to down to minus Vsat. So in this way, so this is the our input waveform here when V reference is negative, and this is the output waveform when V reference is negative. And in these two curves, here we can see that in this case, in the first case when V reference is positive, for these two cases V in is greater than V reference, and for these two cases V in is less than V reference. Similarly, for these two cases V in is greater than V reference, and for this case V in is less than V reference. Okay, so we should be marking the positions or the locations where at the output waveform where the V in is greater than or less than V reference. So therefore the amplitude of V in must be large enough to pass through V reference if the switching action is to take place in this case. That means there should be a very distinct swing with respect to this reference voltage level of the alternating signal's amplitude over or below it, so that it can be very well identified or perceived by the op-amp in such a way that it should switch its output from either positive saturation or to negative saturation and vice versa. So the swing of the input alternating signal should be very distinct with respect to the amplitude of the reference voltage. Now for protection purpose of these circuits, there are two diodes which are called protection diodes connected in this way. These two diodes to be connected in this way, and these are called protection diodes. These are called protection diodes. So the role of these two diodes is to protect the op-amp from damage due to excessive input voltage Vin. So if in some way the Vin is having excessive value, we need to protect op-amp from that excessive movement of Vin, and for that these two diodes will help us. Because of these diodes, the difference input voltage, which is VID of the op-amp, we know that is V1 difference with V2, is clamped to either 0.7 volt or minus 0.7 volt, and hence these diodes can also be called clamped diodes. That means, I mean to say that the difference input voltage, because of this V in and V reference at the input VID at the between the two input terminals of op amp, which is VID, this much. So this should be clamped to either 0.7 volt, because if it is clamped, if it is enhanced its DC level to 0.7 volt or minus 0.7 volt, whatever, then since these two diodes are connected in anti-parallel way, so for either of the cases, if it is 0.7 or if it is minus 0.7, whatever, these diodes will be, one of these two diodes will be forward biased, and that will pass the current through it, because since it is forward biased, it will be conducting heavily, and therefore it will not allow any current to move because of that excessive voltage VID into the op amp, and thereby the op amp will be protected. So for whatever case, if this VID is clamped to two values, one is 0.7 volt or minus 0.7 volt, for the two values, these two anti-parallel diodes, either one of them will take up that challenge to pass the excessive current due to excessive change of input voltage Vin through it, and thereby the op amp will be protected and it will not be damaged. And that's why these two diodes are called protection diodes or clamp diodes. Now there are some op amps with built-in input protection also. In such op amps, the input diodes, these two input diodes are not necessary, where there is in facility of input voltage protection already inbuilt inside the op amp. But if it is not there, then we should be using external to the op amp this type of diode connections, which will working as clamp diodes, because if in some way, because of variation of input voltage, VID is generated between the two input terminals of op amp, and if that generated VID providing the minimum barrier potential 0.7 volt or minus 0.7 volt, whatever, to any of these two diodes, these two parallel diodes, then once getting this value across it, the voltage which is 0.7 volt, the diode will be obtaining its cut-in voltage, and thereby they may conduct. So they may pass the excessive current due to variation of Vin, excessive variation of Vin through it, and therefore it will not allow anything to pass inside the op amp. Okay, so in this way, by using these clamp diodes, we need to ensure that these diodes should be getting at least this 0.7 clamp voltage when there is excessive variation, a clamp voltage from Vin when it is having excessive variation in it. The resistance R in series with Vin, this resistance R in series with Vin is used to limit the current through the two diodes D1 and D2. So this is diode D1 and this is diode D2. We can name as such. So this R is current limiting resistor, which will limit the current through D1 and D2. And to reduce the offset problems also, in this particular type of op-amp configuration, a resistance ROM approximately equal to R is connected between the non-inverting input and the the inverting input and the V reference. So this resistance, this is the current limiting resistance, and this resistance is nothing but my offset minimizing resistance. This is ROM. So this will minimize the offset problem. Offset minimizing resistance. It will work in that fashion to minimize the offset problems. Now let us explain this operation of op-amp when the Vin is applied to the inverting terminal and not at the, and the V reference is applied to the non-inverting terminal. So let us see how that circuit will work. So let us now draw the comparator in inverting mode. This is inverting mode comparator. Last one was non-inverting mode because the input signal was applied to the non-inverting terminal. Here we will be applying the input signal to the inverting terminal, and it is in this fashion. So this is Vin through R. It is connected to the inverting terminal, and at the non-inverting terminal it is connected to a variable resistance in this way. So this is producing the V reference voltage, and this is RP, the potentiometric resistance or the variable resistance denoted by RP, and this resistance is connected to minus VE in one direction and plus VCC in another direction, in this way. So that means we are fixing the reference voltage either positive or negative, deriving that voltage from either plus VCC or minus VE. And between these two, the protective diodes are obviously there, the two input terminals or the clamp diodes, protective diodes or clamp diodes. This is D1 and this is D2, as usual, as we have seen in the last case or the previous case, and the output is VO taken across load resistance RL. So this is the inverting mode comparator. So here the we can see here that the reference voltage V reference is applied to the non-inverting the V reference is applied to the non-inverting terminal, and the V in is applied to the inverting terminal, and V reference is obtained through a potentiometer RP that forms the voltage divider with the DC supply voltages plus VCC and minus VCC. So actually here RP along with plus VCC and minus VE are voltage divider circuit producing reference voltage Vref reference voltage. And when it is derived more from minus V, the Vref is negative. When it is derived more from plus VCC, V reference is positive. So for more on plus VCC, Vref is greater than 0. For more on minus VE, from where the V reference is derived, it is less than 0 or negative. So now let us move on to see the operation of this circuit, and but before that we need to say one thing, that as this wiper of this potentiometer is moved towards the minus V, that is when it is more on minus V, this one, then the V reference becomes negative, and when it is moved towards plus VCC, so it is when it is moving towards this side, V reference is positive. So to a movement of wiper towards this side, V ref is greater than 0, and movement of wiper to this side, V ref is less than 0. Okay, so this is important. Now, thus a V reference of a desired amplitude and polarity can be set up by simply adjusting the potentiometer here. Now, with a sinusoidal input waveform, the output waveform can be similarly defined as we have seen the case in case of non-inverting mode of operation. And now let us see first when V reference is positive, how the input output waveform is look like. So this is T and this is V in. So this is Vp and this is minus Vp, and this is 0 volt. Now let us first place V reference over here. So this is V reference, which is positive here. So for case 1, considering V reference greater than 0 or positive, so here what we will see that when till the time V in is less than V reference, that is up to this, the output waveform should be something like this. So now let us move on to this. When V in is less than V reference, that means the inverting terminal is having lesser voltage, less positive voltage than non-inverting terminal. So that means the output will be starting from positive saturation. So suppose this is plus V sat and this level is minus V sat. So output will start from positive saturation up to the point when it is crossing, the V in is crossing the V reference. Once it is crossed, V in is greater than V reference, so that means input voltage at non-inverting terminal is more positive than voltage at non-inverting terminal, so output will be switching to negative saturation. So immediately it will come down and it will hold the negative saturation level till the time it is once again the V in is once again going down the V reference level, and the output will be immediately switching to positive saturation, and it will maintain that level, or it will stay at that level till that time, till that point when once again V in is greater than V reference, and it will move on to negative saturation once again and reach here till the time it will maintain that level up to this line, and it will once again switch now to positive saturation. So in this way we can find this output waveform. So this is input waveform and this is output waveform, and these two levels for which V in is greater than V reference. So these two levels will mark V in is greater than V reference in this case. So therefore we can write when V reference is taken positive and V in is greater than V reference, then VO move on to minus V sat, that is approximately equal to minus VEE. Okay, and when V in is less than V reference, VO is plus V sat, that is approximately equal to plus VCC. Okay, now let us see what happens for case 2 when V reference is less than 0, that is negative. So let us see that. Now this is the input waveform, this is T, this is V in, this is VP, this is minus VP, this is 0 volt, and let us mark the negative V reference voltage here. So this is minus V reference. Okay, so now here let us draw the output waveform now. So this is VO, and now from here we can see that case 2, when V reference is less than 0 and when V in is greater than V reference, what will happen here? Now when V reference is negative, this is a negative value, and V in is greater than V reference, so therefore it is already a negative value, and V in is far more negative than the negative V reference value. So what will happen? The output will be moving towards the negative saturation because of more negative input voltage. So therefore in this case, when V in during this portion, within this portion, from 0 to up to this portion, when V in is greater than V reference, that means V in is more negative than the negative V reference value, then we can say the output will be moving into the negative saturation. So it will start immediately from negative saturation. So this is minus V sat, and suppose this is plus V sat. So it will hold in that negative saturation till the time V in is coming down the negative V reference value, and it will stay here between these two. So in this case, when V in is greater than V reference, output VO is minus V sat, and that is equal to minus VEE, because input voltage is more negative than the negative reference voltage, so output will be at negative saturation. Now when input voltage within this portion, the input voltage is when input voltage is more positive, rather, just a minute, in the previous case, when input voltage is greater than this negative reference voltage, V in is greater than minus V reference. Here it should be written like this. So within this portion, 0 to minus V reference, the input voltage is greater. So input voltage V reference is more positive than this reference voltage. Input voltage V in is more positive than this reference voltage negative reference voltage. So that means if at the inverting terminal the voltage is higher than the non-inverting terminal, output will be at negative saturation. Therefore VO equal to minus V sat, and the waveform is starting from 0 and maintaining the minus V sat level till the time the input voltage V in is going more positive than the negative reference voltage. So now the voltage at the non-inverting terminal is more negative with respect to the negative reference voltage. So more negative voltage means the output will be, since it is inverting terminal, the output will go to positive saturation, so it will switch at this point to positive saturation and plus V sat. So when V in is less than minus V reference, the output will be switching to plus V sat, which is approximately equal to plus VCC. Okay, and maintain that level till the time it is once again going, the V in is going up the minus V reference up to this value. So here we can say during this portion it is V in greater than minus V ref, and in this portion we can write V in is less than minus V ref. Now at this point, when it is once again V in is moving over negative reference voltage, it will come down to negative saturation, and it will maintain this level of negative saturation up to this point. So it will be like this, and from there it will once again switch to positive saturation. So in this way, this is the input waveform, and the output waveform can be found or can be drawn when, for case 2, the reference voltage is negative, that is applied in the inverting mode of operation. So this is all about the working of basic comparator, considering its inverting and non-inverting both mode of operation, and also considering the reference voltage as positive, as well as negative. So based on this basic comparator operation, we will be let us find another application for this basic comparator, which is called zero crossing detector. Zero crossing detector is nothing but the same circuit which we have discussed right now. It is the same circuit, only the difference is the reference voltage in this case is equal to 0 volt. The reference voltage which we have set to explain the inverting and non-inverting mode of comparator at 1 volt or minus 1 volt for positive or negative value. In this case, if we set the reference voltage at 0 volt, the comparator circuit that is evolved is called zero crossing detector. That means the input voltage which will be compared, the Vin, which will be compared with V reference equal to 0 volt, when the switching will happen between the positive saturation and the negative saturation, when the input voltage Vin will cross the reference voltage 0 volt, either in the positive direction or in the negative direction. That's why this circuit is called zero crossing detector. So zero crossing detector is basically a basic comparator and nothing more than that. It is basically a basic comparator circuit where the reference voltage is set at 0 volt, and the comparison is done in that way that when Vin is greater than 0 volt or Vin is less than 0 volt, that means when the Vin is crossing the 0 volt in the positive direction here and in the negative direction here, and accordingly that has to be counted with the switching from plus Vsat or minus Vsat, or positive saturation, switching between positive saturation and negative saturation. This zero crossing detector can also be called sine wave to square wave converter. As you can see, we are at the input we are providing a sine wave and we are getting a square wave at the output. So this type of comparator is also called, zero crossing detector can also be called sine to square wave converter. Okay. Now let us see the inverting comparator to be used at zero crossing detector, its circuit, the output voltage waveform and all. So let us first draw the circuit of zero crossing detector considering inverting mode of operation. So this is the basic comparator in the inverting mode, because we have applied Vin through resistance R, which is the offset minimizing resistance, into the inverting input terminal. So obviously this is a zero crossing, this is a basic comparator in inverting mode, and this is R that is connected in the non-inverting terminal. And the point to be noted here that there is no V reference DC source is shown in this circuit. So therefore V reference is considered here as 0 volt. So this is 0 volt, and this is load resistance RL across which the output voltage is seen. The protective diodes can be drawn like this. as usual. So these are protective diodes. So as usual, you can compare this with the previous circuit. Our previous circuit was this one. You can see from here everything is same, only this V reference voltage is not applied. This voltage divider circuit is not used, therefore we have considered V reference as 0. So this circuit and this one is same, only the difference to be noted is V reference is no voltage source or potential divided circuit or DC voltage source in terms of reference voltage is used. That's why in this circuit we have considered V reference as 0 volt. Okay, now so this is the basic circuit. Now let us draw the input output waveforms. So this is input waveform. Suppose a sine wave. Obviously we will find a sine to square wave converter. This is 0 volt. Now here we should not be marking any DC level or as the reference voltage, because this 0 volt axis is my V reference here. V reference equal to 0. That means whenever this V in will be crossing this 0 volt axis, it will be a switching in the output of the op-amp. So the output waveform will be look like this. This is T. Now you can see from here, when this V in is in the positive half cycle greater than 0 volt. So when for Vref equal to 0 volt, when V in is greater than 0 volt, that is the reference voltage. What we can see from 0 to up to this point, the voltage input is more positive with 0. So the output should be at negative saturation. So from this point to up to this point, it will be remaining at negative saturation. This is minus V sat. But whenever it is in the negative half cycle, so in the negative half cycle from this point to this point, the input voltage at the inverting terminal is more negative than the non-inverting terminal, so output will become positive. That means the switching will be from minus V sat to plus V sat, and it will stay inside that interval during the negative half cycle here. And once again it is crosses to go above the 0 volt axis, so this will be again switching to minus V sat and maintain its value till this the positive half cycle is completed. So up to this point, and then again it will switch. So this is the output waveform, which is a square wave, with respect to input waveform, which is a sine wave. And the condition is when V in is greater than 0 volt, VO is minus V sat, approximately equal to minus VE, and when V in is less than 0 volt or V reference or 0 crossing towards the negative half cycle, then output will be plus V sat, which is equal to plus VCC. So that means the switching from minus V sat to plus V sat and vice versa is obtained whenever this input V in sinusoidal signal is crossing the 0 volt axis. So therefore this circuit is a marker when the input voltage is crossing the 0 volt axis. That's why this circuit is called zero crossing detector or sine wave to square wave converter. Now there are some limitations in this circuit. In some applications the input voltage V in may be slowly changing waveform, and that is a low frequency signal. So therefore it will take V in more time to cross this 0 volt. Therefore the output voltage may not switch very quickly from one saturation level to another. On the other hand, so this is one problem if it is a slowly moving waveform, the V in. On the other hand, because of the noise at the op-amp's input terminals, there may be noise. The output VO may fluctuate between two saturation voltages. That means when there will be noise, the output will be fluctuating between these two saturation levels, and that fluctuation may sometimes occur very quickly. Detecting zero reference crossings for noise voltages also. So when noise will be present, then it may be that the detection of zero crossing will be based on Vin and both the noise voltage as well. So because the two types of voltage, Vin and noise voltage, both is being applied at the input of the op-amp. So we can say that for both as the input signal, there will be two types of zero crossing detection, and as a result of that, the switching between the two saturation levels may become faster. Or in other words, we can say the noise voltage triggering will be a false triggering. That means it will be a false switching between the saturation levels if noise is detected for zero crossing. Okay, so both of these problems can be cured with the use of positive feedback or regenerative feedback in this circuit. As this circuit is working in open loop, so there is possibility of using feedback, and if it is positive or regenerative feedback, that causes the output VO to change faster rather being slow, and thereby it will eliminate any false output transitions due to noise signals at the input. So that means the slow change will be cured in some way because of the using positive feedback, and that will make the circuit to work faster, so that the output switching between the two saturations level may become fast, and therefore the noise problem and the slow moving problem, slow changing waveform problem of Vin may be countered. So this is all about the basic comparator and zero crossing detector. I hope you have enjoyed. Thank you.